This is the third lecture on Text Unit 7, which is on molecules and bonding. Alright, we have learned in the first two lectures how to make Lewis structures, including those with exceptions to the octet rule. In this lecture, we will look at formal charge in Lewis structures and electronegativity. Alright, first of all, let's define what is formal charge. Formal charge is a number that can be assigned to an atom in a Lewis structure. It's not really a charge, but it can tell us something about where electrons are in molecules. Alright, here is the definition, or how to find the formal charge. Formal charge is found by taking the number of valence electrons of the atom, which again you can take from the periodic table, subtracting the number of bonds to that atom in the Lewis structure, and also subtracting the number of non-bonding electrons on that atom. Alright, so for example, let's look at the ammonium cation, which, as we've already seen, has 8 valence electrons, and here is the Lewis structure. If we look at the hydrogen atom, it has 1 valence electron, 1 bond, no non-bonding electrons. So its formal charge is 1 minus 0, or 0. And likewise, each other hydrogen atom would have a formal charge of 0. The nitrogen will have a formal charge, which can be found by taking its number of valence electrons, which is 5, subtracting 4, which is the number of bonds, subtracting 0 because there are no non-bonding electrons, and obtaining a positive 1. So the formal charge on the nitrogen is positive 1. The total of all the formal charges, 1 for the nitrogen, 0 for all the hydrogens, is 1 plus 0 plus 0 plus 0, or just 1. The sum, it's a rule or a fact that the sum of the formal charges for all the atoms in a molecule always equals the total charge. So the sum of all our charges gave a 1. Note the total charge of ammonium is 1. Alright, let's move on and look at another example. Here, I show a correct Lewis structure, or I should say structure, for the SO2 molecule. There are 2 resonance structures, as I've shown here. Alright, if you assign formal charges to all the atoms in, say, the Lewis structure on the left, this oxygen has 6 minus 2 minus 1, 2, 3, 4, or a formal charge of 0, 6 minus 2 minus 4. Sulfur has 6 minus 1, 2, 3 minus 2, or 1. Charge on the sulfur, formal charge on the sulfur is 1. Formal charge on this oxygen is 6 minus 1, minus 1, 2, 3, 4, 5, 6, or 6 minus 7, for a total of negative 1. Likewise, if you assign formal charges to this Lewis structure to this resonance structure, this oxygen has a negative 1 charge, this sulfur has a positive 1 charge, and this oxygen has a formal charge of 0. Again, these are all formal charges. In both resonance structures, the sulfur has a formal charge of 1, so that is its formal charge for this Lewis structure. However, notice that here the oxygen on the left has a charge of 0, and here its charge is negative 1. Formal charge, the true formal charge, is an average, which is found in just the same way an average bond order is found. Add up the total, 0 plus negative 1, divide by the number of resonance structures, which is 2. Formal charge on this oxygen atom is negative 1/2. Likewise, the correct formal charge on this oxygen atom is negative 1 plus 0 divided by 2, or negative 1/2. Notice that whichever resonance structure you pick, the formal charge is summed to the formal charge of the molecule, which is 0. Alright, what is formal charge for? We can calculate a number for any atom in a Lewis structure. Even though these charges are not real complete charges like in ions, they may indicate fractional charge, or you might think of it simply as places where electrons spend relatively more or less time. So for example, if you look at NH4, you recall the nitrogen has a formal charge of positive 1. Turns out, this nitrogen atom really does, in the real molecule, have a good-sized fractional positive charge, delta positive, where delta is less than 1. It doesn't mean it's an ion, it just means the electrons tend to spend more time around the hydrogen. Not quite enough time around the nitrogen to balance or totally neutralize the positive charge of its protons in the nucleus. So it has a fractional charge within in the molecule. The most common use of formal charge is to analyze different resonance structures. I should say one of the most common uses of formal charge. Lewis structures with separated positive and negative charges indicate less stable arrangements than Lewis structures with smaller or no formal charges. Having a separated positive and negative formal charge positive and negative charge takes energy. So if a Lewis structure has positive charges, has formal charges, is compared to a Lewis structure with no formal charges, the Lewis structure with no formal charges is better. We'll go to an example here in a moment. First, note that in some cases, molecules we've already looked at, it's not possible to draw structures without formal charges. In that case, you're simply stuck. Let's look at an example, however. Go to our example. Draw a Lewis structure for HNCO. Hint, resonance occurs, so you should draw more than one. Alright, attempt that before you move on. The atoms are connected. HNCO. When you add up the valence electrons, there are 16. And there are 3 ways of putting 16 valence electrons into the structure, satisfying the octet rule for each atom. 2, 4, 6, 8, 10, 12, 14, 16 electrons in this structure, and you'll find 16 electrons in these 2 other structures as well. Hydrogen always has 2 electrons through sharing each. Nitrogen atom has 8 through sharing. Each carbon has 8 through sharing, and each oxygen has 8 through sharing. So there are 3 resonance structures for HNCO. Now, using what you know about formal charges, assign formal charges to all the atoms in each structure before moving on in the lecture. Right, when you assign formal charges to these three resonance structures, this is the result. The one on top, well, all of them, note the formal charge on the hydrogen atom is 0. 1 minus 1 minus 0. Here, the nitrogen, and note that the formal charges in all the carbon atoms are also 0 in these resonance structures. The top structure, however, has a positive 1 formal charge for the nitrogen and a negative 1 formal charge for the oxygen. The middle structure has no formal charge for the nitrogen and oxygen. The bottom structure has a negative formal charge for the nitrogen and a positive formal charge for the oxygen. These two structures with separated formal charges are less stable than this and may be discarded. This is the preferred structure. This is the quote-unquote best structure. This is the way the electrons are actually arranged in the molecule. Right, before leaving formal charges, let's look briefly at the carbon monoxide molecule. Correct Lewis structure is shown down here. If you assign formal charges, you obtain a negative 1 for the carbon and a positive 1 to oxygen. They sum to 0, which is the total. That's good. We've discussed fractional charges before. This carbon actually has a fractional negative charge, and this oxygen has a fractional positive charge. This is an example of a quote-unquote polar bond. There's a positive and negative end. Another word for something with a positive and negative end is a dipole. A polar bond is a dipole. If you've had vectors in math, a dipole is actually a vector quantity. They're defined for this course so that we draw them or represent them by drawing a vector or arrow pointing at the negative end of the polar bond or dipole. So carbon monoxide is a polar bond and carbon is the negative end. There's another, generally more reliable way to find polar bonds, and that's using a quantity called electronegativity. What is electronegativity? It's a number assigned to each atom. There are various scales that you would see in various chemistry textbooks. A measure, what it's supposed to be is a measure of an atom's attraction for electrons. In other words, the higher an atom's electronegativity, the more it attracts electrons. These scales assign the same number to an atom in every situation, so you can just look up the atoms in a table. You could look up electronegativity values in a table. However, electronegativity follows the same periodic trends as ionization energy for the same reason. As you go across the periodic table, the nucleus pulls more strongly on the valence electrons because the positive charge of the nucleus increases. So just as ionization energy goes up, electronegativity goes up. Likewise, as you go down a column of the periodic table, electronegativity goes down, just as ionization energy goes down, because the nuclei have less attraction for the outer electrons as they get farther from the nucleus as you go down the table. Electronegativities are typically not defined for noble gases. On any scale, fluorine has the greatest electronegativity. The electronegativity of fluorine is 4 on the Pauling scale. If you know about electronegativity, it's easy to predict if a bond is polar, and which end is positive and which end is negative. If you have two atoms of the same element bonded together, two oxygens, there can be no electronegativity difference, and the bond is not polar. take this situation when you have a nitrogen bonded to an oxygen. Oxygen has a greater electronegativity, which you know because it's to the right of nitrogen in the periodic table. Therefore, there is a partial negative charge on O and a partial positive on N. Oxygen, the more electronegative element, pulls electrons away from the nitrogen, so it has more. And nitrogen has fewer electrons, or the electrons don't spend so much time around nitrogen. Alright, so this creates a polar bond with a positive and a negative N. If you attach a phosphorus to a nitrogen, nitrogen is above phosphorus on the periodic table, has the greater electronegativity. This is again a polar charge, but this time the partial negative charge is on the nitrogen. It's pulling electrons away from the phosphorus atom. Again, you can always show an arrow pointing at the negative end of the polar bond to indicate the dipole. Now, if we attach a phosphorus to an oxygen, the electronegativity of oxygen is greater than phosphorus. Since we know the electronegativity of nitrogen is greater than phosphorus, the difference in electronegativities between phosphorus and oxygen is which means that there will be a bigger partial negative charge on the oxygen, and this bond is more polar than either an NO or an NP, nitrogen-phosphorus bond. Electronegativity is more useful in general than formal charge for predicting polar bonds. It's very rarely, quote, wrong. It happens for carbon monoxide, though, and I should draw your attention to it because it's the example we looked at earlier. Even though this is the more electronegative element, oxygen is more electronegative than carbon. The formal charge situation with this molecule compels the dipole to point toward carbon. Carbon is the more negative end, even though electronegativity would predict that oxygen is the more negative end. So in the case of CO, formal charge predicts the right polarity and electronegativity predicts the wrong direction for the dipole. Now don't make too much of this case. In pretty much every other situation, you will be able to rely on electronegativity to determine the polarity of bonds. Alright, this ends the third lecture for Unit 7.